Hey guys, it's Dr. McJunkin. Happy Friday. Welcome to the last day of week 5 of online learning. Today we're going to talk about limits again, like we did last time, but this time we're going to be looking at limits algebraically. So what does that mean? That means we're not going to be looking at tables or graphs anymore, but we're just going to be looking at equations and can I find the limits of these equations? Okay, so for algebraic limits, for a lot of fantastically nice functions, functions that we'll call continuous that you'll hear about next year. For continuous functions, functions like that don't have holes or vertical asymptotes or jumps like we saw in some of the graphs last time, they're just like nice smooth curves that you can like draw with your pencil without having to pick it up. All we have to do to find a limit algebraically is just to plug in the value that you're finding the limit towards. So literally for most functions, that's all you have to do. Like what we saw with the numeric or the table one last time, where we could just plug in 2 and we found the same limit as we found using the table. Great. It didn't work out when we had a hole in our function because we couldn't plug in that value. And we'll talk about what happens with that later in this lesson. So let's go ahead and just jump in with some simple, easy, quick examples of finding limits algebraically where we just need to plug in the function value. So what does it mean when I want to say plug in the value? The value that I'm plugging in is the value of x that I'm approaching. So that's where we're going to find the value of x that we're plugging in. And then we plug it into the function that is after our limit. So the first one's kind of weird. This is the limit as x approaches 3 of 5. This is the function y equals 5. Which is just, if you think about it, it's just a line at y equals 5. Let me get a different color here. So the function y equals 5, if I can draw a straight line, looks like this, where it's just a straight line at 5. And I want to say, what value am I approaching when I get close to 3? Well, it's just a straight line. So it's approaching 5 from both sides. So if I'm looking at the limit of just a constant value, doesn't matter what value of x I'm approaching, the function is always going to be 5. I can't plug in any x here because there is no x in the function, it's just the function 5. So great, that number goes straight over there. The limit as x approaches 2 of the function 4x squared plus 3. So what does this value, what does this function get close to? What y value does it approach when x gets closer to 2? Well, go ahead and just plug in x equals 2 and see what value the function takes on at that time. And that should be 19 here. 4 times 4 is 16 plus 3, so 19. I can do the same thing over here. Just plug in 1 to this complex function. I get 1 squared plus 1 plus 4 over 1 plus 1, where I plugged in x equals 1. And I get 6 over 2, or I can say, well, that limit value is 3. And then we can even do some trig ones. The limit as x approaches pi over 2 of sine of x is sine of pi over 2. And that value is 1. The key thing for AP Calc next year is you're almost going to always, like 99.9% of the times, is you're going to be in radians. Calculus does not often deal in degrees, always be in radians, like pretty much 99.9999% of the time. Great. Okay, so that's easy. Just plug it in. You can do that. That's basic, just algebra 1 stuff. What if things go badly? There's some things that could go wrong. The main thing that's going to go badly is when we plug in our x value, and get denominator equals 0. So if we want to plug these values in and we get a denominator of 0, that's going to be undefined, like one of those, like the second example from last time, and we can't do that. I can see right away that all 3 of these ones are going to be like that, because if I try and plug in x equals -3 here, -3 plus 3 is 0. 0 in my denominator, bad. If I plug in 2 for the second function, 2 minus 2, 0, bad. If I plug in 1 for this third function, 1 minus 1, 0, bad. So I can't just plug these numbers right in. Our main tip number 1 the one that I always go to first, is factoring. If there's a way to factor and cancel things out and simplify, that's what I want to do. Okay, so when I'm going to look at this function, x squared plus x minus 6 over x plus 3, I see I have a quadratic in my numerator, so I'm going to factor that. So this is going to be the same thing as the limit as x approaches negative 3, and it's key to keep this limit notation. So the limit notation is going to stay until I can actually plug in this value of x equals negative 3. So this limit up here is equal to the limit of something where I'm factoring the numerator. The x plus 3 won't factor, but I'm going to factor my numerator, and that should factor into x plus 3 times x minus 2. That should be a pretty easy quadratic factoring. These will cancel. And so this is, again, still equal to the limit as x approaches negative 3 of x minus 2 over 1. Whenever I cancel things out here, I get a 1. But the 1 won't really matter. And then once I'm ready to plug in the x value, because I won't get 0 in my denominator anymore. I've got a 1 down there. Once I'm ready to plug that in, I can get rid of the limit notation and just plug in negative 3 for x. So negative 3 minus 2. If you want to keep it over the 1, you can, but that's just negative 5. Cool. So if I can factor, cancel, and simplify, and then you kind of find the limit. What's going on here in our actual graph is like what we saw last time, where I have a hole in my graph, and canceling these factors out is what kind of gets rid of that hole to tell me exactly what value I'm approaching. Okay, so the limit as x approaches 2 of x squared minus 4 over x minus 2. Well, the denominator is not going to change, so I'm going to say limit as x approaches 2. My denominator is going to be x minus 2. But I can factor the numerator. It's a difference of squares. And I can factor the numerator to x plus 2 times x minus 2. So 2 and negative 2, numbers that multiply to negative 4, but add to 0 because there's no middle term. The x minus 2s are going to cancel again. So this is the same thing as the limit as x approaches 2 of just the x plus 2. Dividing it out, I just get a 1 in my denominator. And then I can go ahead and plug it in. 2 plus 2, hopefully that is 4. I've done my math correctly, which I probably did. Well, let's look at the last one. The limit as x approaches 1 of 2x minus 2 over x minus 1. I don't have a quadratic in my numerator, but I do have something in my numerator that does factor, because my denominator is not going to factor. The x minus 1, I can't change it. But I notice that in my numerator, I've got a common factor of 2. So if I factor out that 2, I get 2 times x minus 1, and that is what's going to cancel out the x minus 1 in my denominator. So then I get the limit as x approaches 1 of 2, but this is just a constant function again, like my first example, so it doesn't matter what value of x I'm approaching. My function's always going to be approaching the value of 2, because that's what it always says. One more factoring one. Oh, we love factoring. So now I've got quadratics on both the top and the bottom. Let's go ahead and again keep this limit notation every time until I'm ready to plug in x. And I need to factor both the top and the bottom. Pause for a second if you want to try to factor the top and the bottom yourself. Otherwise, I will go into what I have here. So the top should factor to x minus 2 times x minus 2. The bottom should factor to x minus 2, x plus 3. One of the x minus 2's cancels out with this x minus 2 in the bottom. I can't cancel out both. So I just cancel out 1. This is the limit as x approaches 2 of x minus 2 over x plus 3. And once I'm ready to plug in my value of 2, because I know it won't change my denominator to 0 anymore, I can just go ahead and plug that in and get rid of the limit notation. So 2 minus 2 over 2 plus 3, where I just plugged in x equals 2. I get 0 over 5, which is just 0. So my function, even though it's undefined at all these points, does indeed have a limit. So even though if I try to plug in 2 right away here, I would have gotten 0 over 0. I can cancel some things out and then get an actual answer of 0 over 5, which is just 0. As long as 0 is not in my denominator, I'm cool. Okay, Two other techniques that don't come up as often, but they will come up sometimes, is polynomial division and rationalizing. So tip number 2 is polynomial division. I have the limit as x approaches 1 of x cubed minus 1 or x minus 1. Oh my gosh, this is the example from last time that we looked at. Okay, so I know that bad things happen at 1, and I actually know the answer because we've done this one. The answer was 3 using the tables. So what I need to do, though, is actually divide out this polynomial. So I'm going to use polynomial long division here. X minus 1, x cubed minus 1. I wanted to actually divide this out and see what I get. So polynomial long division, what times x would give me x cubed? Well, that's x squared. X squared times x minus 1 is x cubed minus x squared, and I subtract. I'm not going to go too much into depth with this because this is a skill that we should already kind of have, is dividing these out, just a basic reminder. So x cubed minus x cubed should give me nothing there. The negative negative x squared will give me a positive x squared, and I bring down the negative 1. Okay, so what times x gives me x squared? Well, that's positive x. And then I multiply the x by both these terms. I get x squared minus x, and I subtract. X squared minus x squared is nothing. Negative x is positive x, bring down to 1. And I see that x times 1 will give me x, so plus 1. 1 times x minus 1 is x minus 1. And this one should fully cancel out to 0. Let's move this over so you can see that end part there. So at the end, I got x minus 1 here, so it cancels out, and I get 0 as my answer. So there's no remainder. It divides out perfectly. So this is then the limit as x approaches 1 of this divided by this is just the function that I got here up top. X squared plus x plus 1. Now there's no denominator, so I can just easily plug this in. 1 squared plus 1 plus 1 is 1 plus 1 plus 1, or 3. We saw that last time. Okay, and the last fun, crazy trick is rationalizing. So let's give myself as much space as possible here. Okay, so I see that I have the limit as x approaches 0 of this crazy function with square roots in it. But right away I can see, hey, I can't plug in 0 because my denominator is just x. So what I'm going to do is I'm going to multiply the top and the bottom by the conjugate of this crazy radical expression. So what does that word conjugate mean again? Well, it's just the radical expression where everything is the same except for the sign in between the radical and the non-radical. So I'm going to multiply the top and the bottom by the square root of x plus 1 plus 1. The square root of x plus 1 plus 1 on the top and the bottom. Let's go ahead and multiply. This might be not the nicest, but square root of x plus 1 times square root of x plus 1, they're the same things. Square roots cancel, so I just get x plus 1. Great. Square root of x plus 1 times positive 1 is just positive square root of x plus 1. Now I distribute this negative, so negative 1 times square root of x plus 1 is negative square root of x plus 1. Hopefully you see some nice things that are going to happen. And then negative 1 times positive 1 is negative 1. In my denominator, I'm just going to leave it like this, x square root of x plus 1 plus 1. When you see problems like this, you'll realize you don't actually want to distribute the x. We'll see why in a second. And this is what we have now. It looks way worse. That's okay. Look, this cancels and that cancels. Great. This cancels and that cancels. Great. Let's rewrite, because we just canceled a lot of stuff. This is the limit as x approaches 0 of the only thing that's left in my numerator is x. And my denominator is x times square root of x plus 1 plus 1. Cool. Now I can actually cancel this x and that x. So this is the limit as x approaches 0 of 1 over square root of x plus 1 plus 1. Okay, that was a lot of multiplying and canceling. We're almost there. Now I can see that if I plug in 0, I'm not going to get 0 in my denominator because of this plus 1. So I can go ahead and do that. 1 over square root of 0 plus 1 plus 1. And that's just going to be 1 over square root of 0 plus 1 is 1. So 1 plus 1 is 2. So I'm just going to write here the square root of 0 plus 1 is just 1. Square root of 1. Another key thing that I kind of glossed over just to make sure, like when you divide out something from the top of the bottom, you're left with the 1 here in the numerator. Don't try and cancel these out and then say you're left over with 0. When you're dividing the x by the x, you get 1 in the numerator. Okay, so my answer here then going back is 1/2. So my function undefined at that point, but it's approaching 1/2 from both the right and the left. This is really powerful in the fact that we can find what's happening to this function even though at that point the function is undefined. There's a hole there, there's a jump, there's something. But we can find a limit here because it gives us a nice value. You can divide out that discontinuity there. Okay, go ahead and rewatch the video, take notes if you need to. If you've got questions, I'll be online to answer email questions from 9:30 to 11:30, and I will be online for virtual office hours from 2:45 to 3:45. I'll see you there. Otherwise, have a good weekend. See you next time. Bye, guys.